In this section, we'll talk about properties of ZP, the ring of p-adic integers. Recall that the ring of p-adic integers ZP is the inverse limit of AN, where AN is the ring Z mod PNZ. Specifically, the elements in ZP are infinite sequences, satisfying the compactability condition that phi sub n plus 1 of x sub n plus 1 is equal to xn. This phi sub n plus 1 is the natural map from Z mod Pn plus 1z to Z mod Pz, induced from the identity map on Z. If you don't like this language and prefer elementary number theory language, we can also restate this compatibility condition as follows. Equivalently, this condition is same as saying xn plus 1, if you view that as an integer, is congruent to xn modulo pn. And now, remember from the definition, this infinite sequence X has components in Z mod PNZ. And another way to look at this is that to view all of them just as integers. And this compatibility condition is equivalent to saying that as integers, xn plus 1 is equivalent to xn modulo pn. And you can further extend this to xm congruent to xn modulo pn for any m bigger or equal to n. And now let us discuss the properties of ZP. We consider the following map. Let epsilon sub n be the map from ZP to AN, where this map is a function that associates to an p-adic integer x to its nth component. In other words, this is a projection of ZP onto its nth component. The first proposition is about the exact sequence associated to the ring of p-adic integers. We have that the following sequence is the exact sequence of abelian groups. And here, the map epsilon sub n is a projection onto the nth components we just defined. And this Pn map is a multiplication of elements here by Pn component-wise. This multiplication by Pn is a abelian group homomorphism, but it is not a ring homomorphism. That is why we call this sequence just the exact sequence of abelian groups. Because we do not have something like Pn times x times y is equal to Pn times x times Pny. This is not necessarily true. But we do have the Pn times x plus y is equal to Pnx plus Pny by the associativity in the ring ZP. This is true, but this is not necessarily true. So we only have an abelian group homomorphism, not a ring homomorphism here. And as a consequence, we have the following identification. Notice that the image of ZP under this multiplication by Pn is Pn ZP. So we have the isomorphism ZP mod PNZP. The image here is a kernel of epsilon sub n. So this quotient will be isomorphic to the image of epsilon sub n, which is an. And an is z mod pnz. So this exact sequence will give us the following identification. Before we start proving that the sequence is exact, there's one thing we need to clarify. We need to clarify why this p to the n is a well-defined map. Namely, why does it preserve the compatibility of sequences here? For any compatible sequence, x in ZP, y is pnx, again in ZP. This is very easy to see, but still, to be rigorous, we need to check this. Indeed, since x is compatible, we have phi sub m plus 1 of x sub m plus 1 is equal to x sub m in am. Remember, equivalently, this is the same as x m plus 1 viewed as an integer is congruent to the integer xm modulo p to the n. And now, if we multiply both sides by pn, what will happen? This congruence equation will hold modulo pm plus n. And in particular, it also holds modulo p to the m. So we have the compatibility of this sequence. Therefore, this map is well defined. And now we start proving this proposition. The exact answer here is very clear, because epsilon sub n as a projection is always onto surjective, so it is clearly exact at this position. Now suffices to verify that it is exact here and exact here. First, we're going to show the multiplication by p is injective as a map from ZP to ZP. And then as a consequence, because p to the n can be viewed as the nth iteration of the multiplication by p. So the multiplication by pn is also injective. So how do we verify this? Indeed, if x is a p-adic integer and satisfies p times x is equal to 0, then p times each component xn plus 1 is equal to 0 in an plus 1 for any n greater or equal to 0. And this means if we view xn plus 1 as an integer, then it is divisible by p to the n. So we can factorize xn plus 1 as follows. And then we take this equation, which is defined in Z, back to an plus 1. And now we're going to use the compatibility. By compatibility, we have xn plus 1 is congruent to xn modulo pn. But xn plus 1 can be written as pn times yn plus 1. So xn is congruent to pn yn plus 1 modulo pn. But this guy, modulo pn, is congruent to 0. So xn is congruent to 0 modulo pn. That means xn is 0 in an. And because n is arbitrary, we have the x is 0. So this verifies the exactness at this position, because multiplication by Pn is injective. Now let's check the exactness here. This time, we're going to verify that the image of the multiplication by Pn is same as the kernel of the projection onto the nth component. It is easy to see that the image of the multiplication by Pn is always contained in the kernel. This is because for any element x in ZP, Pnx will automatically kill the first n components, because this guy is equal to 0 modulo p to the n, and this is equal to 0 modulo p. So they automatically vanish in their corresponding components. And in particular, this guy will be projected to 0. So this element always lives in the kernel of epsilon sub n. And now conversely, we want to verify that the kernel is also contained in the image. We want to show that we have this containment. Suppose we have an element that lives in the kernel. Then its nth component must be 0 in an. And it follows from the compatibility that x minus 1, which is phi n of xn, must be 0 in a minus 1. And inductively, you have that x1, which is the image phi 2 of x2, is equal to 0 in a1. a1 is z mod pz. And hence, this element will actually take the following form. Its first through the nth components are all equal to 0. And non-zero terms can only start from the n plus 1th position. And now we claim that xn plus k is congruent to 0 modulo Pn for any k bigger to 1. Why this true? Indeed, this is nothing but the compatibility of this sequence. This is because that xn plus k is congruent to xn plus k minus 1 modulo p2n plus k minus 1. And you go all the way down to xn plus 1 congruent to xn, which is congruent to 0 modulo Pn. And you put all these congruence equations together, because those powers are higher than Pn, we have that xn plus k is congruent to 0 modulo Pn. Now, what does this claim tell us? This claim tells us that xn plus k is divisible by Pn. And as a consequence, we can factorize xn plus k as a product of Pn and another integer. And this is for any k bigger or equal to 1. And now remember, our goal is to show that this kernel is contained in the image. We started with the element in the kernel, and we are trying to find another element in ZP whose Pn multiple is precisely equal to x. And now we have more or less found what we needed. Now let y be the infinite sequence formed by those yks. And next, we're going to first show that y is a compatible sequence, so that it indeed lives in ZP. And Pn times y is equal to x we started with. First, we're going to show this y lives in ZP. Namely, we have the compatibility condition. And remember, this compatibility condition is equivalent to saying that yk plus 1 is congruent to yk modulo pk for any k. Why is this true? Indeed, by our construction, we have that xk plus 1 plus n is p to the power n times yk plus 1, and xk plus n is p to the power n times yk. Since x is compatible, we must have xk plus 1 plus n congruent to xk plus n modulo p to the k plus n. And plugging in these two equations, we have Pn times yk plus 1 and Pn times yk are congruent modulo pk plus n. And now, if we divide both sides of this congruence equation, we have yk plus 1 congruent to yk modulo pk. And that is exactly what we want. So this verifies the first claim. And second, we're going to show that Pn times y is indeed equal to x. So the y is a pre-image of x under the multiplication by Pn map. Remember, the x takes the form of where the first n components are all zeros, because it is in the kernel of the projection onto the nth component map. So the first n components are all equal to 0, as we discussed from here. Now clearly, Pn times yk is always congruent to 0 modulo Pn. And actually, it's congruent to 0 modulo pk as well for any k from 1 to n. This means this vector y, after multiplied by Pn, has the first n components vanish as well. And now, for any k bigger or equal to n plus 1, by construction, we have Pn times yk is equal to n plus k. This is our construction. And by the compatibility of x, we have that xn plus k is congruent to xk modulo pk. So Pn times yk is equal to xk as element in ak for any k bigger or equal to n plus 1. Therefore, we have verified that for any component of y, if we multiply that component by Pn, it is always sent to the corresponding component in x, which means y is indeed a pre-image of x under the map Pn. And this finishes the verification of the exactness at this position. And thus, this completes the proof.